So there are two things in our Canvas that I would really, really appreciate all of you doing. One is more for me, one is more for you. So the first one is there is a short survey to evaluate the course. I would really appreciate it if all of you did this. It's definitely like, it's kind of the only way I get evaluated by students. So it's also anonymous. I won't know who fills out the survey. So it's at the top of the modules in Canvas. Next time you're in there, please click on it. Follow the survey. It takes like 5 minutes. It just asks you about like what I did well, what I could do better, things you like, things you didn't like, so on and so on. I definitely do read the comments eventually, although not until after the quarter is over. Again, they are anonymous, so I won't know who is saying what. So if you think this was terrible, not that I really think that, but I'm just saying you can write whatever you want. It's totally fine. And then, but yeah, my boss does see them, so like they are important. Like I don't get like, it's not like she'd be like, James, a student wrote a bad thing about you, you're fired. Like nothing like that. But like just like I get to see them. I want to know what I can be doing better. Really, is what I'm really going for here. So let me know. Let me know what's good. Let me know what could be better. All that. The second thing, which is more for you all, is that there is a quote unquote quiz. It's not really a quiz that I'd like you all to take. It's really a survey. Yeah, there's a survey. When are you taking 17B? So I would like to know when you all are taking 17B or if you all are taking 17B. So depending on if a lot of you are taking it in summer session 1, I might try to offer more specific support for 17B. So please let me know when you're taking it, just so I can kind of plan accordingly for the future. That's all. I will say this again when there are more people here or next class, whatever. All right, that's that. Then, as far as what we're doing today, so I feel like your homework's out of order weirdly, right? Like section 3.6 got moved back to being due when, like June 5th, whereas section 4.1 is due June 2nd. I could maybe potentially see her moving that section back as well, but I feel like we should kind of plan accordingly. So my idea for today is we're going to go briefly over the exponential growth stuff, and then we'll still have time on Thursday to revisit it if we need to. And then we'll mostly spend today talking about section 4.1. So that's my plan. Obviously, if you have specific questions you want to ask from the homework or in general, you're welcome to. But I'm going to start talking about exponential growth and decay, because it's not too terrible, and it's kind of like the same thing every time, just a few different ways we can ask the same sorts of questions. So let's look at the following. So exponential growth and decay. So the main idea of exponential growth and decay is that we have some exponential growth formula. And the formula for exponential growth is / decay is we have y equal to c e to the k-t, where y is the amount of stuff at time t. And stuff could be people or bacteria or radioactive material or whatever we are measuring, right? It's just how much of the thing we're talking about do we have at a certain time. And then over here we have C, which is typically the initial amount or initial population. We have T, which is not surprisingly time in whatever particular measurement of time. It could be seconds, hours, minutes, weeks, months, years, whatever we feel like measuring time in. And then we also have this number K here, which is kind of a weird number. Welcome, come on in. We're just talking about exponential growth and decay. And so I'll point out K is typically called actually, what is K called? The rate of growth? Sure. No, it's the relative growth rate, I think. Yeah. K is called the relative growth rate. We'll talk about that in a second. K is the relative growth rate. And specifically, if K is positive, then we have growth. Things are getting larger as time goes on and on. And if K happens to be negative, we have decay. Here's what's important about this equation. this equation actually comes from a differential equation. And it comes from, well, in fact, let's just take the derivative of both sides. If we take the derivative, we're going to get, well, you've got c times e to the stuff. C is a constant multiples hang out. And the derivative of e to the stuff is going to be e to the stuff times everybody. Thank you. And what's the derivative of k times t? Which one's the variable? The k or the t? T, right? We know t is the variable because I said dy dt, right? That dt in the bottom is telling us, oh yeah, we're differentiating with respect to the variable t. And so the derivative of a constant times t is just going to be that constant. Okay, but check this out. This thing here, c e to the kt, that is what y was equal to. So really, this equation here, the solution comes from the differential equation dy dt equal to k times y. The reason I'm pointing this out is because the next quarter in 17B, we do talk a fair amount about solving differential equations. And a differential equation is just an equation where you have a function y and one or more of its derivatives, dy dt. So I just want to point out that for this differential equation, this is the solution. This is the solution to this differential equation. So I know it's not super important right now, but I just want to emphasize when you're solving a differential equation next quarter, your solution is a function. Okay. So yeah, cool. So the nice thing about this is we know that if our function, our exponential growth or decay looks like this, it had to have come from a differential equation that kind of looked like that. For example, if we have that dy dt equals 3 times y, we know what the solution looks like. We don't have, and so I should give you a little more context. There's a reason why we specifically emphasize this particular example is because when you get to 17C, this specific differential equation is kind of the basis for most of what you do that quarter. And so that's kind of why we're saying, okay, well, if we have this kind of thing, the solution is going to look like this because it's going to come up a lot in your future. So if we have this, it can't, or the solution is y equal to ce to the 3t. We don't know what c is yet because no one told us how much we were starting with, but that's the solution. Or for example, if you had dp dt, the rate of change of the population, equal to 0.05 times p, then we would end up getting p equal to ce to the 0.05 times t. You don't have to use t. You can really use whatever letter you want. So for example, if you had, say, dA dx, where x is the independent variable and a is the function or the output, equal to, say, negative 2.01 times a, that would mean that a as a function of x was equal to ce to the negative 2.01x. But the pattern is the same every time. If your rate of change is a multiple of your function, that means your function has exponential growth or decay. Here's what I would like you to also see about this, because I think it's important. What we're saying really here is like the rate of change of y is 3 times y. So if y represents, like, say, the number of bacteria in a, in a cell or whatever, well, my biology is not good. Don't listen to the biology part. Number of bacteria, right? Then we're saying, okay, well, the rate at which the bacteria is changing is 3 times the number of bacteria. So the more bacteria we have, the faster they're going to grow because there's more bacteria to make more bacteria faster. That's the whole idea here. That's why you get exponential growth or decays, because things are growing faster and faster because you have more and more of them to make more and more of them. Same deal here. We're saying the rate of change of population is 0.05 times the population size. So the population gets bigger, then you are making more people faster. Now, all of this to say is that in each of these problems, this number here that we're multiplying by our function is k. And in each of them, if we solve for k, here's what we get. So for example, right here, if we solve for k, we get that dp dt divided by p is equal to 0.05, which is our k value. And this is called the relative growth rate. So when someone says, what's the growth rate? Well, I can tell you that the population is growing at 500 people per year. And you might say, James, that is not very helpful. You're talking about the population of the world, or Davis, or San Francisco, right? It's all in context. So to know what the actual meaningful piece of information is, we say, well, give me your growth rate and divide it by how many people there actually are. Because that's actually meaningful. If I say that the relative growth rate is 0.05, that means I'm growing at 5 people per every 5 people per unit of time per every year. Or sorry, I almost said that. I almost said it right. I blew it at the end. So right here we're growing at say like 5 people per unit of time, let's say per year, per every 100 people. That's what this relative growth rate is saying. It's saying how fast the population is growing per the population size. And that is definitely a more useful piece of information. Again, if I said we're growing at 500 people per year, not meaningful, because you don't know how many people there are. So usually in some of these homework problems I'm looking at, you are being asked for the rate of growth after a certain amount of time. I'm sure there's a relative growth rate problem in here somewhere, I hope. Maybe. Yeah. Oh, yeah. Right off the bat. Very first question. Cool. Okay. So let's look at a few more kind of more concrete examples here. Yeah. So let's say we have, oh, yeah, I should give you all the language too. So here's an example problem. A bacterial culture initially contains 100 cells and grows at a rate proportional to its size. I'm going to underline that. After 3 hours, population is 500 bacteria, I don't know. It's not a language class, it's not a biology class. Nobody cares. Okay. Question A. What is the population after T hours? Okay, this question here that you will probably see sometime is really just a way of saying, tell me what the function is. Find y of t equals c e to the kt and fill in the constants k and c. But I want you to know, because there's like 3 different ways people are going to phrase this. One way that you will know something is exponential growth or decay is when someone says the population grows at a rate proportional to its size. Right? That's literally just what we were saying. All of these populations were growing, right? Their rate of growth was proportional to their size, right? Rate of growth, multiple of size. Rate of growth, multiple of size. Rate of growth, multiple of size. So that's one way of cueing you into the fact that we have exponential growth. But there's another way of saying it. Another way someone could say this is, they could say the relative growth rate is constant that literally means the same thing, just with different words. And if we look at this, it's true. Look back at our example. In each of these cases, if we solve for the relative growth rate, the rate of change divided by the population, you would always get a constant value. And it'd be 3 or 0.05 or negative 2.01 respectively. And then another way of saying it is the growth is, this is kind of the most obvious way, the growth is exponential. So these three phrases all mean the exact same thing, that the growth is exponential. And you should say, okay, if I see any one of these three things, I know that that means I'm going to start with y equals c e to the kt. That is what that really all means. When we see any of those magic phrases, we know it's going to be exponential growth, and you're going to do y equals c. Or you can use, I mean, I like y and c to the kt. You could say a equals p e to the rt, or n equals n not e to the k. Right? You can use whatever letters you want. This is pretty standard. Sometimes if you're talking about like the mass of something, you use m equals m not e to the kt, but really the letters don't matter. It's the same function every time. All right, so when we write this question, what we really mean is solve for c and for k. And here's what I think is the best thing to do. Make yourself a little table. Right, your times over here and your y values over here. And we should have 2 times with 2 known y values, and then a third thing where we're either trying to find the y value or the time. Except we won't here because we're just finding the function. So let's see, if I read the question, a bacterial culture initially contains 100 cells. Okay, great. At time equals 0, the population is 100. And I'm going to plug that in. Now, I should say, when you have this particular time times 0, you can probably skip this step and just know that your c value is going to be whatever that initial value is. But you can also show the work. If I plug this in, I get, well, y on the left is 100, and I get c e to the k times t is 0. K times 0 is 0, e to the 0 is 1. So I really get 100 equal to c times 1, or 100 equal to c. Great, I found my c value. Now I'm going to plug that in. I'm going to write y equals 100 e to the kt. That's my refined model. I'm getting closer to the actual function I want with the constants filled in, but I'm not done yet. I still have to figure out what k is. So I should usually have some other data point. My other data point here is that 3 hours later, so when time equals 3 hours, the population is now 500 bacteria. So y equals 500. Great, so now I'm going to plug that in and see what happens. I'm going to plug it into the refined model. So over here in this refined model here, my y value gets to be 500. I get 100 instead of c, right? Because I know that c is 100. E to the k times t, which is now 3. And now I can use this equation to solve for k. So solving for k, I get, let's see, I'm always going to divide by this coefficient here first. So 500 divided by 100 is 5. So 5, believe it or not, equal to e to the k times 3, or I would probably write 3 times k because it's more normal to write it that way. And then we would take the natural log of both sides. So the natural log of 5 equals the natural log of e to the 3k, but the natural log of e to the 3k is just 3k. So the natural log of 5 equals 3k. And finally, natural log of 5 divided by 3 is equal to k. And you stopped right there, and this was the question. I would probably knock off a point or two because we haven't answered the question yet. The question is, what is the population of CRs, meaning write y equal to c to the kt with the correct c and k value plugged in. So our final answer here for this question should be, it's kind of unruly to write. It's going to be y equal to 100 e to the k, which is natural log of 5 divided by 3 times t. In fact, I made it look terrible there. That is our answer to this first question. Questions about what we've done so far? For T? Well, we did. Well, because the question is, what is the population after T hours? They didn't specify a time. So this question could also be phrased as find population. I'm going to call it Y as a function of time. That's really what this says. It's just written in my opinion, not my favorite way, but it is often how it's written. When they ask you the question, what is the population after T hours? They mean, tell me the population for any value of T. Or in other words, write the population as a function of time, where I can now give you any time value and you can tell me what the population actually is. But there isn't a T value to plug in yet until we ask the next question. The next question is, find the number of bacteria after 7 hours. And I should specify, and usually there, when we say after a certain amount of time, we mean 7 hours from the initial time. AKA, we're going to set T equal to 7. This is the easiest version of the question we can ask, right? Once we found the model, which is what we just did, or the function, then if you are asked to find the population at a certain time, it's really easy to just plug in T equals 7. So here's our model, Y equals 100 e to the, I forgot what my K was, natural log of 5/3, yeah. Times T. And now if I want to find what T of 7 is, I'm saying Y, when I plug in T equal to 7, it's going to be 100 e to the natural log of 5/3 times 7. And honestly, there's not much more you should do here. You could use a calculator to get an approximate value. I wouldn't, not for web work. Web work doesn't want an approximate value. This is what web work wants for sure. So I would leave it like that. It's not the best, but it's what we have. The more interesting question we can ask is, when will the population reach 2,000 bacteria? Or more generally, what time is it when we reach some number of bacteria? So now we're not setting the time equal to 2,000, we're setting Y equal to 2,000. So here we are setting Y equal to 2,000. So if my equation is Y equal to 100 e to the natural log of 5/3 times T, then we're going to say, okay, well, that's going to become 2,000 equal to 100 e to the natural log of 5. And now we're going to solve for T very much like how we solved for K. We're going to divide by this coefficient. We're going to take the natural log of both sides, and then we're going to solve for what's left over. So dividing both sides by 100, we get 20 equal to e to the natural log of 5/3 times T. And then we take the natural log of both sides. And we could, although I feel like you can skip this step, but if you wanted to, you can write natural log of 20 equals the natural log of e to the natural log of 5/3 times T. If you feel like we've had enough experience with things to know that we take the natural log of e to some stuff, you just get stuff. So I would encourage you all to skip that intermediate step and say, oh, we know that the natural log of 20 is just going to be the natural log of 5 divided by 3 times T. Okay, and then I could divide both sides by natural log of 5 over 3, but I'd rather multiply both sides by 3 over natural log of 5, so I don't have fractions and fractions. So I would say that 3 over natural log of 5 times natural log of 20 equals 3 over natural log of 5 times natural log of 5. I would never show this stuff really, but do. Cancel, 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 cancel. And then we finally get time is equal to 3 times the natural log of 20 divided by the natural log of 5. Interesting. Sorry, I'm just having a thought here. No, that's not true. Okay. Yeah, right. Yeah. Okay, anyway, yeah. What? Well, sure. So it's really just like, what if I was solving like 7 equal to 3 11ths times t? What would I multiply both sides by? I mean, I can divide both sides by 3 11ths, right? I can definitely say 7 divided by 3 11ths equals 3 11ths times t divided by 3 11ths. And then those will cancel. But when you divide by a fraction, how do we simplify that? Right, we multiply by the reciprocal of the denominator. This is more just the work that you would do instead of just saying, oh yeah, I know I have to multiply. But yeah, you could totally do this, or you could say, I'm going to multiply both sides by 11/3. I guess the question or the answer I could have given is, what's 11/3 times 3 11ths? Well, 11 times 3 is 33. 3 times 11 is 33, and 33 over 33 is 1. The same thing is true over here. 3 over natural log of 5 times natural log of 5 over 3 is 3 natural log of 5 over 3 natural log of 5. Those cancel out to give you 1. So we end up getting. Okay, so here's a question that I feel like doesn't usually get asked, but except it always gets asked in this particular class is, what is the rate of growth after 4 hours? Okay, when you see these words, rate of something, you should immediately think of the derivative. So what they're asking us here is, okay, I know that y equals 100 e to the natural log of 5 over 3 times t. And now they're asking me, I want to find dy dt evaluated at t equal to 4. Okay, there's an easy way to do this and a less easy way to do this. The less easy way is just to take the derivative. Okay, well, I know how to find the derivative of e to the stuff. Dy dt is going to be 100 times e to the stuff times the derivative of that stuff. But the derivative of a constant times t is just the constant natural log of 5 over 3. If I want to plug in 4 and say dy dt evaluated at t equal to 4, I'm just going to substitute in 4 for t. And I'm not going to simplify. I'm going to leave it looking kind of awful. It's going to look like 100 times e to the natural log of 5 over 3 times 4 times the natural log of 5 over 3. I don't like it. I mean, it's fine, but I don't really like it. Another way to go about this is to say the following. We already know that dy dt is equal to k times y. That was given at the very beginning, right? The actual problem said the growth rate is proportional to the population size. This is exactly what that says. Growth rate is proportional to population size. And we know that our K value is natural log of 5 over 3. So we can say that dy dt is equal to the natural log of 5 over 3 times y. Y of t, if you want to make it more explicit, that y is a function of t. And so then if I want to plug in 4, I can say, okay, well, dy dt is equal to the natural log, oh, sorry, evaluated is equals 4, is the natural log of 5 over 3 times y of 4. You still get the same answer, like it's not really less, but it is less work and you not have to think about taking the derivative because we already know what the derivative is based on where this thing came from. Sometimes in homework problems, they will give you what the function is at a particular point and ask you to find the derivative at a particular point, but they won't actually tell you what the function is. And so this is kind of how you're supposed to do that. Here, we're going to get the natural log of 5 over 3, and then y of 4, plug in 4 to my function here, I get 100 times e to the natural log of 5 over 3 times 4. Very much the same, written very slightly differently. A slightly different way of thinking about getting there. Okay. So, as much as I would love to talk about this more, I do feel like we should talk about the other stuff because that stuff is probably due Friday. At least currently is due Friday. So let's go. So we'll certainly, if we need to, and I think we should talk about this stuff more on Thursday, we will. But let's go ahead and talk about the other stuff that's due on Friday, just so that you have time to get started on and work on it if you haven't already. Yeah, cool. I know it's kind of fast, but we should go the other way. So let's talk about the following. Let's talk about, sure, absolute maximums and minimums. Sure. So we can find these by graphing. For example, find the absolute max and min of f of x equal to, I'm going to make it easy, I'll take it easy, x squared on the interval from -2 to 3. We can totally graph this. We know what x squared looks like. We can certainly stop it at -2 and 3. So here's what my graph is going to look like. -2, +3. And let's see, if I plugged in -2 squared is +4. And then if I plugged in 3 squared is +9. And it has the usual parabola shape that hits the origin as its vertex. It looks something like that. It's a little straighter looking than I want it to look. Oh well. We're pretending it looks like a parabola. We can all pretend. Okay, so it's going to take 2 hands, but show me on your fingers. What's the biggest y value I've got? See some fingers. I know 2 hands. Yep, 2 hands. Yep. Okay. Yep. Exactly that many. My biggest y value is 9. Okay, great. So here's what we would say: the absolute maximum is a value of 9. Additionally, I can say the absolute maximum occurs at x equal to 3. So the max value or the minimum value is the y value, and the where it is whatever the x coordinate is. And it is possible, although not in this example, that you could have more than one x value associated with your absolute maximum. Right? If I had said, what's the absolute max of this function on the interval from -3 to +3, then you would have had a maximum both at -3 and at +3. And that can happen, that's okay. You can definitely have more than one absolute maximum if they all have the same maximum value. The absolute minimum is what value, everybody? How low do we go? It's 0. It also occurs at 0. So the absolute minimum occurs at x equals 0. I should probably be more explicit here. Absolute maximum is a value of y equals 9. Absolute minimum is a value of y equals 0. So just be careful when you're doing questions like this, because sometimes they'll ask you where the maximum or minimum is, and that's the x coordinates, or they'll ask you what the value of the maximum or minimum is, and that's the y coordinates, or the function value more general for not graphing. Sometimes people like to ask questions that are, I don't want to say dumb because that's not nice, but dumb, not dumb, just, I don't know, pointless in my opinion. We could say, find the absolute max / minimum of, sure, f of x equal to 2x minus 3 on the interval from -1 to infinity. Okay, great. So I know how to draw that line. I'm like, do I? If I plug in -1, which is kind of the starting point, for lack of a better term, -2 minus 3 is -5. I'm starting at, and that's kind of low here. So here's my starting point at -1, -5. And then I'm going up and to the right. Sure, kind of like that. My graph is not the best. Okay, the minimum value is, all right, let me ask you all, is the minimum value on your left hand -1, on your right hand -5? Minimum value, I want to see a hand, left or right, left or right. -1 on your left, -5 on your right. -5. The minimum value is -5. The place it's occurring at is at -1. So the value is y equal to -5. It occurs at x equal to -1. When you hear the word value, you should think y value. Those go together. Two peas in a pod is. Yeah, that's kind of an old movie. Anyway, maximum value. Okay, what is the biggest numerical value that this function gets to? So infinity is what we want to say, except we can't, because infinity is not actually a real numerical number. So instead we say that there isn't a maximum value. Because what would you have, like, if I tried to say the maximum value was 1 billion, you'd be like, well, James, it's 1,000,000,001. And you guys 1,000,000,002, right? Someone else could always find a higher real number. And we can't ever say that the maximum value is infinity or negative, because they aren't real numbers. So the maximum value is, there isn't one. This function is unbounded above. It just gets larger and larger and larger. Yeah. Okay, let me ask one more annoying question, then we'll get to the real kind of meat of the stuff, which is, let's say, ooh, yeah. Sure. Let's say my function f of x is equal to, sure, 9 over x minus, sure, now I have to think of a number. Sorry, my brain doesn't want to work. X minus 2 on the interval from, yeah, I'm going to be real unkind about it. On the open interval from 5 to infinity. Let's draw the whole function. This function 9 over x minus 2 has a vertical asymptote where? Yeah. We'd have a vertical asymptote x equals 2. I guess I could find the y-intercept as well. If I plugged in 0 for x, f of 0 is 9 over -2, which is -4.5, like somewhere down here. So it looks something like this. The usual kind of hyperbola. It's shifted 2 to the right, it's stretched kind of by a factor of 9. There's the actual. We want to start at kind of 5. Which if I plugged in 5, 9 divided by 5 minus 2 is 9 divided by 3, which is 3. Let me graph for you the section of this graph that we actually get and watch how it's going to be annoying. So move over to 5, 1, 2, 3, 4, 5, up to 3. They don't actually get the 0.5 comma 3. So my graph kind of looks like it has this open circle there, and then it's going to get smaller and smaller and smaller as a horizontal asymptote getting closer and closer to 0. Why do I always pick 5 and 3? Numbers I'm the worst at actually writing clearly. Good question. All right, so I'm going to ask you some questions that have non-answers. I'm not going to ask you, I'm just going to say. So if we ask what's the maximum value of this function, we don't get 3. It's open, right? Because I did an open interval here, not a closed interval here. So do we ever actually get to 3? No. Okay, great. So someone want to venture a guess at what the maximum value is? Right, there's none. Someone might try to say, well, James, it's 2.999. Well, it's 2.99999. Someone's be like, well, more nines, more nines, more nines. Someone might say an infinite number of 9s. And they're like, oh, but that's the number of 3. So it's kind of weird. And this is something that we shouldn't spend too much time on, even though I would love to, because it fascinates me all the time. But it is technically true. If this blows your mind, you should come talk to me later. The 2.999 forever is not approximately, is literally actually the same number as 3. I know that might seem weird. But if you are confused by this, and I was confused by this the first time I learned it, so you wouldn't be like, there's no shame in being like, James, that seems really wrong. I don't know if I believe you. Here's one way people kind of prove it to themselves. What's the decimal expansion for 1/3? 0.3, 3, 3 forever, right? What if I multiply both sides by 3? What's 3 times 1/3? Okay, what's 3 times 0.3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3. It always has 3s. It never has any other number. It's all the 9s, right? There's no ever anything to carry because we never get a number that's bigger than 9. So it really, and now there are more like proofy proofs of this, but it's really true that 1 is equal to 0.9 decimal forever. And the reason this is actually true really is that 2 numbers are the same as each other is if there's no number between them. There is no number between 0.99 forever and 1. So they actually the same. It's kind of like, although very less challenging than, it's kind of like how 8/2 and 4 are the same number, just written different ways. These are the same number, just written different. Okay, back to the actual stuff we're doing. I just sorry. I get there, I'm like, anyway, if you want to talk about this more, come see me. So absolute maximum, we don't have one. Because we never quite get to 3. Absolute minimum, we don't have one. Because we never quite get to 0. So not every function has an absolute maximum or minimum unless we meet some certain requirements. So here are the requirements we need to guarantee a function will have an absolute maximum and minimum. And it's called the extreme value theorem. Extreme. The extreme value theorem says the following. If f of x is continuous on the interval that we're looking at, call it AB, on the, I should say, on the closed interval, then f of x has an absolute maximum and absolute minimum. In the interval. So here's how we do this in practice. In fact, let's just do an example. So let's say, I'm going to use the same example I used earlier today, which is totally fine. Let's look at the following example. Let's look at the function x cubed minus 6x squared on the interval from -1 to 7. You could graph it using Desmos and see what it looks like. But the problem is eventually the graphs become, I don't know, challenging enough that it might not be easy to see where your actual highest y value and actual lowest value is. And or the values might be gross decimal approximations in Desmos, whereas you actually want the real accurate value in your report. So here's the process. We're going to find the critical values What's the critical value, you ask? The critical values are where the derivative is either equal to 0 or undefined. So we're going to find where f prime of x equals 0 or f prime of x is undefined. So let's see here. If I take my function, f of x equal to x cubed minus 6x squared, f prime of x is going to be 3x squared minus 12x. And I'm going to set that, well, I'm going to note it's never undefined, right? It's a nice quadratic. Quadratics are defined. Polynomials are defined everywhere. So if you see something, if your original function is a polynomial, you don't have to worry about checking where it's undefined. It's never going to be undefined. But we do need to check and see where it's equal to 0. And to do that, we typically want to factor. So I factor out a 3x. I'm left with x minus 4. So I'm going to get x equal to 0 and x equal to 4. And those are the places on our function where we're going to have a horizontal tangent line. But then it also could happen that we have this thing maxed out at one of the endpoints. For example, I'm going to flip back to my parabola example for just a second to show you. So start looking at the very beginning here with our parabola example. You could have an absolute maximum at the endpoint where the derivative certainly isn't 0. Right? If you take the derivative of x squared, you get 2x, and you plug in 3, the derivative there is like 6. But you could also have an absolute extrema, whether maximum or minimum, at one of your critical points where the tangent line has a slope of 0, or you have a horizontal tangent line. So any critical point where the derivative is 0 has to be checked to see if it's absolute max or min. And any end point also has to be checked because maybe that's where you have the biggest or the smallest value. And that is how we usually, if we don't have some, I should say, if we're looking for an absolute max or a minimum on a closed interval, this is how we typically do it, where we find all the critical values and we check your endpoints and your critical values and see which one's the biggest and which one's the smallest. There are some questions in your homework that say, like, look at the graph because your interval is kind of weird or maybe goes to infinity. Those ones aren't this where you're finding all the things and checking each of them by plugging them in. You're just kind of looking and seeing, oh, where's the biggest, where's the smallest. But we could graph these if we really wanted to do that. It's just, this is a more, it's a faster, this is a nicer way of doing it if we have all the things we need to make it happen. So thing 2, plug in each critical value and endpoint into your original function. So we're going to find f of 0, f of 4, f of -1, and f of +7. And to make your life easier, I would recommend, it's almost always worthwhile to factor this as much as possible. So this factors as x squared times x minus 6. So if I plug in 0, plugging in 0 is going to be easy. I'm going to get 0 minus 0. 4 is a little more work. I'm going to get 4 squared times 4 minus 6, which is 16 times -2, which is -32. F of -1, I'm going to get -1 squared times -1 minus 6, which is 1 times -7. Finally, f of 7 is going to be 7 squared times 7 minus 6, which is 49 times 1. So then we look at all these outputs and we ask, which one is the biggest? That one. That's the biggest. Which one's the smallest? That one. So we have, an absolute maximum value of what? What's our maximum value? 49 at x equals 7. You might also say that the maximum is just at the point 7, 49. That is sometimes how people say it, so they can get all of the information in one kind of breath. And then we have an absolute minimum value of -32 at x equal to 4. I always like to say both because I just feel like it's good to give all the information I can. But I feel like most of your homework questions are asking for the value, not for the export. Just FYI. In case you're wondering what this looks like, because I do think it's worth seeing what it looks like. Oops, come on. This function looks like this. Has an intercept at 6 and at 0. Here is my relative minimum at 4, -32. And then at -1, I plugged in -1 and I got -7. That's that part right there. And I plugged in 7 and I got 49. There's -1, -7. There's +7, 49. So you can see that just on this portion, from -1 all the way to +7. Oh yeah, clearly the maximum is right there and the minimum is right there. Let's look at some more. How much time we got? Yeah, we got time. We got time. Let's look at another example. Let's say our function was f of x equal to, sure, x minus 3 to the 2/3 power, 2/3, yeah, on the interval from, let's go from 2 to 11. This function is definitely continuous on that interval, right? There are no breaks. Let's find all the critical points. Critical points. So we're going to take our derivative, f prime of x, and set it equal to, well, find it. So it's going to be 2/3 times my stuff to the -1/3 power times the derivative inside, which is just. Now, before I set this equal to 0, I want to rewrite it because I want you to see what we're going to get. So I would rewrite this as 2/3 times x minus 3 to the 1/3 power, or if you prefer, 2/3 times the cube root of x minus 3. So can this ever actually equal 0? For a fraction to be equal to 0, the numerator has to be 0 at some point. Let me just point out, because I want you all to be down. You're still going to get the right answer here, but I just want you to know why you're getting the right answer. So let me show you something. So can 5/x minus 3 ever equal 0? Definitely not. There's no way ever equals 0. X equals 3 makes it undefined. So x equals 3 makes it undefined. On the other hand, x minus 3/5 equals 0. X equals 3 is a solution. So we always, if you're trying to make a fraction equal to 0, if you're trying to solve where a fraction is equal to 0, it's always setting the top part equal to 0, not the bottom part equal to 0. So this will never equal 0. No solution. However, what value of x will make this thing undefined? Well, what would make us divide by 0? Yeah. If x equals 3, then f prime of 3 is undefined. So even though x minus 3 makes, is not a place where the function is differentiable, this function still has a critical point at x equals 3. And here's why. Here's what this function looks like. I call this the bird function, because it kind of looks like little birds a small person or person not good at drawing might draw, like myself. This kind of looks like x minus 3 to the 2/3. It's just going to be shifted 3 to the right. It kind of looks like this. You can even see from the graph, we have a minimum when x is equal to 3. You can also maybe see from the graph that the function is not differentiable at x equal to 3. We have a cusp, or a pointy point, as I like to say, or a kink, as I think your teacher likes to say. Right, but there's definitely a place there where the function is sharp. We don't have it being differentiable. That doesn't mean we don't have a critical point. We definitely have a critical point at x equal to 3. Okay, so now we do the usual thing. We test our critical point and our endpoints. So I want to find f of 3, f of 2, f of 11. Now, if you look at this thing here, you might be able to already guess look at the function here, what x value do you think we're going to have the maximum at? 2, 3, or 11? Sorry, I'm not good at hearing. Where is the highest y value? At x equals 2, x equals 3, or x equals 11? And where's the lowest y value at? What's that? The value would be 0, but where is the lowest y value at? I think I might have said x is 3. And that's what we're going to get. When we plug in 3 here, you just get 3 minus 3 to the 2/3. And 0 to any positive power is just 0. F of 2 is going to be 2 minus 3 to the 2/3, which is -1 to the 2/3, which is -1 squared, which is 1, and the cube root of 1 is 1. And then f of 11 is going to be 11 minus 3 to the 2/3, which is 8 to the 2/3, which is 2 squared, which is 4. So definitely 0 is the smallest, 4 is the biggest. So the maximum value of 4, a minimum value of 0. There we go. Okay. So let me think here for a second. Sorry, I need to think for just a moment here. I know it's 1 sec. Give me a moment. Let's say we were trying to do the following. Let's say we had, I want to find the absolute maxima and min for f of x equal to, yeah, that'll work. Sorry, sometimes it's 2x cubed plus x squared minus 4x plus 1 on the interval from, let's make it -3 to 0. Oops, you can't see anything I'm writing. Sorry. I know you're all letting me think. I appreciate it. Okay, we want to find the absolute maximum and minimum for f of x equal to 2x cubed plus x squared minus 4x plus 1 on the interval from -3 to 0. So, usual first step if we ask for max. So these are the key things you should be looking for. Absolute maximum and minimum on a closed interval. I guess it's also important that this function is continuous. I should be a little more explicit. Your function does not have to be continuous everywhere. It just has to be continuous on the interval that we're looking at. You can have something that is wildly discontinuous way over at 5 to infinity, as long as it's continuous on what we care about. All right, let's find some derivatives. My derivative is going to be 6x squared plus 2x minus 4. Okay. Quadratic factoring. Well, do we have to factor? Probably. But technically, no. You can solve this if you really want to. Excuse me, by using the quadratic formula. That's always an option if it's quadratic. But I like factoring because it's usually faster. So I also see here that I can factor out a 2 from everything before I do anything else. And then there are like 3 or 4 different ways people solve quadratic equations equal to factoring quadratics when your coefficient isn't 1 here. People like to do this and say, okay, 3 times -2 is -6. And then I got a 1 there. So I'm looking for numbers that add up to 1 and multiply to -6. They happen to be 3 and -2. Now here's the problem with this. I want to make this really quick because I've seen this mistake way too many times to let you make it. What we're not saying here, we're not saying this is equal to x minus 3 times x plus 2. Those are not the same. Right? If you multiply this out, you would get x squared minus 3x plus 2x is minus x minus 6. That's not right. Not at all. So what do we do with this? Like, this is the right idea, but how do we use this to get the actual factoring? Here's the way I like to do it, but if you have a way that works for you, you should do it the way that works for you. But my idea is the following. Take your quadratic here, and I would probably divide both sides by 2, but I would normally just say, I don't need that 2 there. And rewrite your 3x squared plus x minus 2 as 3x squared plus the x is what's going to be replaced by the 3 and the -2, meaning specifically 3x minus 2x. I haven't changed anything, just written it differently. And then when you do this, what will always happen is that then you can factor this 4-term thing using factoring by grouping. The first 2 terms here, I can factor out a 3x from. I'm left with an x plus 1. These second 2 terms here, I could factor out a 2, but that would be the wrong choice because I want what's left over to be the same as here. If I factor out a 2, I'd be left with a -1 minus x. I'd rather factor out a -2 and be left with x plus 1. And then finally, from each of these pieces, I can factor out an x plus 1. So you get 2 times x plus 1 times a 3x coming from here and a -2 coming from here. And that's actually how I do this. And so then we end up getting x equals to -1 and x equal to positive 2/3. Again, I will point out there are many other correct ways of doing this. This is just the way I choose to do it. I'll be really frank. This is actually not what I do. What I really do, it's what I do if the numbers are hard. Here I would have just guessed. Then I'm like, oh, I need to multiply the -2 over here. There's like 2 choices. 2, maybe 4 choices. 2 and -1 or -2 and +1. And then the 3 and the 1 go in different spots. Like I could have probably done it faster by just guessing a few wrong things until I got the right thing. That's also a valid way of going about doing it, but this is a process that will always work. All right, so now here's the fun part about this one. What do I need to check? I need to check f of -3. This is going to be not fun. And then f of 0, which is easy. F of 0 is going to be 0 plus 0 minus 0 plus 1. Do you make sure that you're plugging them back into the original function, not into. And then f of -1, I'll find out. And then f of 2/3, nope, I don't need to do that. And the reason I don't need to do that is because 2/3 is not in the interval. So even if you get a critical value, you only have to actually check that critical value if it's a point that's inside the interval that we're starting with. 2/3 is definitely not between -3 and 0, so we're not going to bother it. And I will tell you, if I were giving a question about absolute maximums on an exam, I would almost always for sure make it so that at least one of the critical points was not in the interval I asked about. Because it's something that's easy for students to overlook, but it's also something that's like they're easy points to get if you just look for them. But you have to actually know what you're doing to get those points. Whereas it's something that's also easy for students to miss. So I would be on the lookout for that. If you have an absolute max or absolute min test question on your final exam, make sure that the points, your critical points you're checking, the only ones you should be taking are actually in the interval that you're looking. Also, 2/3 is a pain to check here. So I'm like, if you see something that looks really terrible to check, that's also a good clue that maybe it's not in the interval. So, so then let's see. All right, f of -3 is 2 times -27 plus 9 minus 4 times -3 is plus 12 plus 1. I actually do need to well, I'm going to wait on that actually. Let me wait and see how the f of -1 looks. F of -1 is going to be 2 times -1 cubed, -2 plus 1 plus 4 plus 1. That's going to be 4. I feel like that's more negative than that, right? Well, in fact, yeah, it's going to be negative, right? This is -54. But they're probably going to ask me the values, so I probably actually need to find it. Okay, fine. 9 plus 12 plus 1 is 22. And then -54 plus 22 is -32. Okay, so here is my absolute minimum value. Here is my absolute maximum value. Oops, wow. Really, James? Really, James? You guys want to correct me on that, or did I just do it myself? Here's our absolute maximum value. Holy smokes. Here's our absolute minimum value. Minimum small, maximum big. Sorry. Okay. Yeah. I'm just wondering about one thing before we keep going here. We have 10-ish minutes left. Yeah, let's talk about one more. Let's say we had something that looked like, okay, so let's say we have the function f of x equal to the square root of x over x plus 1 on the interval from 0 to 4. So again, actually, before I even get started here, is this function continuous on that interval? Yeah, probably. Let me ask a better question. Where is this function discontinuous? For sure. Anywhere else? Actually, everywhere it's negative. Right? We can't take square roots of negative numbers. So this function's domain, right? The domain of this function is really 0 to infinity here. It's definitely not continuous where it's not defined. Okay, let's do the thing. So critical values. Oh man, I gotta use the quotient rule. Okay, it's the bottom times the derivative of the top. The top is x to the 1/2, so the derivative is 1/2 x to the negative 1/2 minus the top times the root of the bottom, which is 1, all divided by the bottom squared. Now I know we've kind of been in the place where we've been like, yeah, we don't need to simplify this derivative. Well, that's no longer the case. To solve these things equal to 0, we really have to simplify them. So if I'm trying to simplify this, I'm looking at factoring out an x to the negative 1. Because it's always going to be the smaller of the two powers of the common thing. Negative 1/2 is smaller than 1/2. So if I do this here, we're going to get x to the negative 1/2 times stuff, and then x is 1 squared on the bottom. Okay, so from this first piece here, I'm still left with an x plus 1. I'm still left with a 1/2. But I don't have an x to the minus 1/2 because I factored it out. Minus, and here's the people I feel like always get a little bit stuck. Here we're going to have an x to the first. The way I think about it is, well, let me ask you a different question. If I was factoring something easy like 3x to the 4th plus 5x to the 7th, what power of x can I factor out from that expression? X to the 4th or x to the 7th? 4th, right? The smaller power, always the smaller power. Okay, so when I factor out the x to the 4th, I'm left with a 3 here plus a 5x to the what? Show me on your fingers. Yeah, thank you. Yes, exactly. How did we get that number? Well, the way I got it was 7 minus 4 is 3. That's the same way we're getting this number. 1/2 minus negative 1/2 is 1. Or actually, what I like to think about is if I multiply it back through, does it work? X to the 4th times 3 is 3x to the 4th. X to the 4th times 5x cubed is 5x to the 7th. X to the negative 1/2 times x to the 1. We add those powers, and negative 1/2 plus 1 is positive 1/2. So it would get us back to where we were. Just be careful with this. It's easy to make mistakes there, but it's not too terrible for just. All right, so then we simplify, which is never the fun part. We get x to the negative 1/2 times a 1/2 x plus 1/2 minus x all over x plus 1 squared. And then finally, I would probably bring this x to the negative 1/2 down to the bottom and write it as 1 over square root of x and times, x plus 1 squared. I don't know why I wrote 1 on top though, because I'm going to have 1/2 x minus x is a negative 1/2 x. So I have 1/2 minus 1/2 x. And I guess I would probably factor out a 1/2. Because why not? Okay. Yeah, we got time. What is the only single value of x that makes this equal to 0? There's only one answer. That makes it undefined. Let me ask a better question. What makes the top equal to 0? Positive 1. So that's going to be x equal to 1. Okay. Now, what are the values that make this undefined? Negative 1 and 0. Okay, but here's an even more refined question. Which of these two is actually a critical point? One of them isn't. You know which one isn't? That one. You know why it's not? Well, we didn't say it, but it's not because it's not in the domain of the original function. It's not even that it's not in like the interval here. It's literally the function isn't even defined at negative 1 anyway. So it's not a critical point because it's not in the domain of the original function. All right, so then, so then we would test the points. So plugging back into the original function, f of 0, we were going to test 0 anyway because it was an endpoint. F of 0 is 0 divided by 1 is 0. F of 1 is 1 divided by 2. And f of 4 is the square root of 4 divided by 5. Sorry. Okay, 0 is the smallest. What's bigger? 1/2 or 2/5? you don't like fractions, use decimals. 1/2 is 0.5, 2/5 is 0.4. And I know I should say one more thing and then I'll be done. So I know we started using critical points just now, and I didn't really define them, although I kind of said what they were, but I want to just tell you because there's something important that I want you to know, and I'll stop talking. Oh, by the way, just for everyone that kind of came in, I said this at the beginning, I'll say it again real quick here. There is a course quiz, which is really just about when are you taking 17B. I would really appreciate you all filling it out just so I can kind of think about how I might best support you if you're doing it in the summertime. And then the other thing I wanted to mention, which was at some point, I would really appreciate it. Also, the answers are anonymous, so I will not know what you've written. I will know what you wrote about me at some point. We'll get to read them. I just won't know who wrote it. So don't feel like you can write whatever you want. It's totally fine. So critical points, what I want to say is for y equal to f of x, c is a critical point of the function if f of c equals 0 or f prime of c equals 0 or f prime of c is undefined. And this is important, c is in the domain of the function. So one quick example here. F of x equal to x squared over x minus 1. What's the only number that's not in the domain of this function? Domain, everything except for x equal to 1. So right off the bat, we all know that 1 can't be a critical point. But the extra real piece of information is that even though 1 isn't going to be an actual real critical point, it's still important to recognize that the derivative is going to be undefined there. And we actually, even though 1 isn't a critical point, if we start graphing these things, which typically we do at this stage, knowing that 1 is a place where the derivative is undefined does become important. So if we take the derivative, our derivative is going to be bottom, derivative of the top, minus top, derivative of the bottom, all of the bottom squared. And check this out, we end up getting 2x squared minus 2x minus x squared over x minus 1 quantity squared, which becomes x squared minus 2x over x minus 1 squared, which factors as x times x minus 2 over x minus 1 squared. And if we set that equal to 0, we get two critical points, x equals 0 and x equals 2. And if we set it equal to undefined, we get x equal to 1, but this is not an actual critical point. It's what, now your teacher might disagree though. Your teacher might be like, yeah, it's a critical point, it's fine. Textbooks kind of go back and forth on this. Most textbooks define a critical point as having to be in the domain of the original function. What it will tell you is that when you're graphing something like this, and you start making your sign chart for your first derivative, which is something we'll talk about either this week or next week, because that's all the time we've got left. When you make your sign chart for your first derivative, you will want to include this on your sign chart because it's an important point. Even though it's not an actual critical value, I usually call them pseudo-critical values because we still want to include them, but they're not places where we can actually have a maximum or minimum because the function has a vertical asymptote there, and you can't have a maximum or minimum at the vertical asymptotes. All right, it's enough for today. See you all on Thursday.